Hello everyone and welcome back to your YouTube channel. And welcome to this very exciting video of today. And as you must be aware, I am recording this video because several of my students in advanced power systems at the master level, they are undertaking some assignments, some homework related to frequency control and frequency stability. So a very important element on frequency control is the understanding of what we call system frequency response model. I know that several of my friends here, they are laughing because we are using in power system the concept of frequency response. So I must tell you that the concept for power engineers, the concept of frequency response for power engineers is a bit different to the concept of frequency response in control theory. In power systems, we call system frequency response to the behavior, dynamic behavior of the frequency in electrical power system when we have a power imbalance inside it. So today, my job here is to try to introduce you to the amazing world of the system frequency response models. So before we start again, I would like to invite you to be part of this amazing social media community for scientists, and that is ResearchGate. ResearchGate is an area where you can find many scientific papers, books, and presentations, and so on. But also is a very wide community, and you have the possibility of asking questions or helping somebody else by answering them. The models that we will be discussing today in this video and also in the coming videos will be located here at the GitHub repository. However, at the moment they are not available for the general public. It will be released probably in 6 months' time. On the other hand, if you are watching this video, of course you are inside the YouTube channel, your YouTube channel, and I call this your YouTube channel because this YouTube channel is dedicated for everyone and every single of you. You are the people making this YouTube channel. And if you like this channel, please subscribe in order to make the community grow. Or if you have any comment, please feel free to leave the comment in the video, and I will be extremely happy to answer your question or to take into consideration your suggestion. Okay? Also, we have a couple social media that if you want to see what we are doing in research, innovation and development, please subscribe to the former Twitter social media now called X. And also we have here the link for LinkedIn. LinkedIn is a very active part of the community where we are releasing a lot of information many times per week. Finally, if you have any comment or you would like to know more about what we are doing, please feel free to drop an email. So before we start this video today, I would like to introduce a very short and very brief background. So something that we need to understand is the term frequency. And frequency is related with AC signals. And that concept is extremely relevant if you are working in electrical power system, because power system in those days, the majority of them, they use AC signals. So if you are in America, probably you need to follow the standard, the IEEE, the Institute of Electrical Engineers. And over there are several standards. One of them is the C57.12. And over there, you can see the definition that I highlight over here. And that the frequency is the number of periods occurrence per unit of time. So if you look over here, we have a perfect sine wave form, and you can see that the period is the time that this signal take to repeat. And you can see over here that the period for this very specific signal is 20 milliseconds. So using this very important equation, you can see that the frequency is calculated as the reciprocal of the period. So the frequency on this signal over here is 50 Hertz. However, if you are based here in Europe, the International Electrotechnical Commission defined the frequency as the reciprocal of the period. So again, it's very simple to see that basically we can have the frequency calculated if we know the period. For instance, here at the bottom right hand side of this slide, we have a signal, and you can see that the period is 5.55 milliseconds. So using this amazing equation, frequency is the reciprocal of the period, so we obtain 180 Hertz. However, we know the concept of frequency, and frequency is a vital parameter in defining the operation of the electrical power system. And when we talk about frequency in electrical power system, we need to understand that there is something called the nominal or rate frequency in Hertz. And is basically the specification of any equipment device that is test condition, and the frequency are based on that, okay? So here on the bottom right hand side, you can see a huge map, and you can see in red color the countries where the frequency is 60 Hz. The majority of the 60 Hz countries are located in America. However, there are few places where the frequency is also 60 Hz, like Saudi Arabia and also South Korea. 50 Hz is also shared in the majority of the countries worldwide. You can see here countries in South America like Chile, Argentina, but the majority of the countries in Europe, Asia, Africa, and Australia, they are using 50 Hz. 50 Hz with a period of 20 milliseconds. A very interesting case, one of the very interesting cases worldwide, is the case of Japan. Japan is, for historical reason, divided in one area that is using 50 Hz, but another area in that country is using 60 Hz. So if we need to interconnect two different frequencies, remember that a direct connection is not possible, so we need to use HVDC. For more information about HVDC system, there are several of the YouTube videos over there that you can see, you can watch over there and understand this. However, we have defined the rate frequency, but every single system during the normal operation, the frequency can be changed based on the balance between generation and demand. And that is because every single utility in the world recognizes that the frequency is a very important indicator related to the balance between generation and demand. From the utility, power utility perspective, frequency is not just the single reciprocal of the period, because time to time measuring that period is a bit tricky. We will not discuss here in this video. There are other videos in the YouTube channel. However, it's very important that you understand that many utilities worldwide, they define the frequency based in the most important balance, that is the balance between generation and demand. So if you see over here in SOE, that is the transmission system operator, one of the bodies of the transmission system operators in continental Europe, you can see that the Appendix 1 is defining the frequency in the network or the system frequency F as a measure for the rotation speed of the synchronized generators. So by increasing the total demand of the system frequency, and of course the rotational speed of the generators will decrease. But on the other hand, if we decrease the power demand, so the system frequency and of course the speed of the generator will increase. National Grid ESO, National Grid Electricity System Operator, that is basically the transmission system operator here in the GB, Great Britain, define the system frequency as a continuously changing variable. You must understand that second by second, millisecond by millisecond, the system frequency is changing. And this frequency is determined and controlled by second in real time by the balance between the system demand and the total generation. If the demand is greater than the generation, the frequency falls. While in generation, if the generation is greater than the demand, the frequency rises. So as you can see, transmission system operators has a more practical, more interesting from the operation point of view definition regarding the frequency. So power engineers, we are constantly interested on calculating, determining, and obtaining the system frequency. In 1990, our very brilliant colleague Paul Anderson published a paper in the IEEE Transaction on Power Systems, and this amazing paper was titled A Low Order System Frequency Response Model. And in this brilliant paper that you can obtain at the IEEE Explorer, he introduced these amazing models that they are dedicated for estimating the system frequency. When I say system frequency response model, is because it's a model where the input is basically a active power deviation, and we obtain at the output a frequency deviation. However, Anderson was very, very clever because at that moment, 1990, he introduced the concept using or considering just the classical electromechanical behavior of the traditional synchronous-based power systems. So if you are considering the traditional power system, that they are only synchronous machine, you must understand that the frequency is moving quite slow. So to be honest, they are very low order frequency response. So as this frequency is moving very slow, we can use linearized models to represent the electromechanical, the system frequency created by the electromechanical synchronous machine. So as you can see, low order, they are representing just the electromechanical behavior of the system frequency. Something that is not realistically if we have power converters. Power converters, they tend to create frequency oscillations in a relative high bands. And also this model is not including oscillations related to voltage or reactive power. So system frequency response model inputs active power and output frequency. This is something that you need to understand. Second, because we are considering only the electromechanical behavior, so we can use linearized system. So from the control point of view, that have an advantage, because we can create linearized models for the system frequency response model. And that is what I will show you in the next slides. In here, I want to show you the system frequency response models. And this is just a brief introduction. I can be here for days and days talking to you about the details of those models, but right now it's just a high level overview of them. For instance, let's start with a very simple model. We can consider a control area, and in that control area we have some generators and some demands, and there are not internal losses between the generation and the demand. So in this slide over here, what I am showing you is a block diagram representing the model of a single area control system without primary frequency control. So as I said before, the inputs over here is the system load change, and the output over here is the frequency deviation. We are using a linearized model, and that is the reason that we have the capital Greek letter over here, delta. So what you need to understand is that when I say system load change, I am talking about the load deviation from the steady state point. And also, as you can see, this model is represented using S, and in this case the variable S is representing what we call in this case the Laplace transformation. Okay, so inside a block diagram we have transfer function inside those blocks, and also we have some adding points, and the arrows are representing the flow signal or the flow of information. So two important parts in this block diagram. One is representing the frequency dependent loads. Something that you must understand, this is not the truth, and here we are representing static loads. And in static loads, when you have some frequency deviation, there is a possibility that the active power consumption can change. So this letter DL over here, that is in units of hertz per megawatts, what is representing is how much the active power will deviate from the steady state point in megawatts when there is a frequency deviation in hertz. So in general words, we are representing over here the system frequency response of the static load. On the other hand, we have here the system inertia. And the system inertia is represented by a transfer function inside this block. And inside this block, you can identify the numerator is defined by the rate frequency of the system, in this case 50 hertz. And in the denominator, we have this very interesting term, twice h, where h is the rotational inertia. S base is basically the apparent power base in your system. And this letter S here in the denominator is very important because remember, S is representing the Laplace transformation, and that is representing a integral. What I am telling you is that 1 divided by S is what we call an integrator. To be honest, this part of the block diagram is basically a modified version of the swing equation, that we have one input that is representing the mechanical power generation change, and on the other side we have, with the minus symbol over here, the electrical power deviation. So when we create the difference between both of them, what we are obtaining here is the deviation or the change on the active power acceleration in the system inertia. Of course, those models has been implemented for different platforms, and those models are located in GitHub in few months' times. We have those models created in MATLAB Simulink, but also using Typhoon Hill. So here there is a step forward because, as you remember, inside the electrical power system we have some loads, and those loads can be dynamic loads because there is a behavior that is changing in a different way when the frequency is changing. So rotating loads like induction motors directly connected to the grid, they have a behavior that is dynamically changing. So we have here 2W0. W0 is a constant that is defined over there. F0 is the rate frequency. And again here, S, the letter S, is representing what we call the Laplace variable over here. So in this case, the rotating mass is using this as a denominator. And if you remember the Laplace transformation, that letter S is representing a differential term. So in other words, the power, active power deviation over here will depend of the derivative of the frequency deviation. Again, here we have one more improvement because right now we are adding the primary frequency control. And adding the primary frequency control is very important because that will show you how the prime mover of your generator is behaving when you have this active power imbalance. So as you can see, we are improving the model. And in this case, we are adding over here a control loop. You can identify here a first order transfer function where here inside the denominator, there is a time constant for the turbine. What I am telling you is that this very important block over there is representing what we call the turbine dynamics and the control. And a very important variable again here is related with the droop. You must remember that the droop is a very important variable affecting the steady state frequency, system frequency. And here we are using the letter R in order to represent how we change the active power generation based on frequency deviation. So this is the model representing what we call a single area control system with primary frequency control. So there are many other system frequency response models for multiple area or including secondary frequency control or tertiary frequency control. Here what we want to do is just a brief introduction. A brief introduction because in the coming video, the next video, I will be implementing one of these very interesting and exciting system frequency response models using a simulation software. So for now, in this video, you understand the concept of frequency, then you realize that the system frequency is a very different concept that the system frequency response that you can get in control theory. For us, electrical power system engineers, the system frequency represents how the frequency of the system changes when we have an imbalance between generation and demand. And also, I show you that those models introduced in 1990 by Paul Anderson, they are linearized models based in that amazing paper that is called a low-order system frequency response model. And also, almost to close this video, I show you that there are different block diagrams. We use block diagrams to represent the low-order system frequency response models. And those models, they can be helpful because they allow us to predict the frequency, the system frequency deviation when we have an active power imbalance. So for now, we are reaching the end of this video, and in the next one, I will show you how to implement one of those control models, and I will see you at the next video, and it's time to say bye now.